Alright, here we're going to show the derivation for the period of a compound pendulum or a physical pendulum. And here's my pivot location, and I'm going to attach a thin rod to its end. And so it has some given rotational inertia. And in class we showed different scenarios where we can vary the rotational inertia by maybe like attaching a disc to the center or a point mass along the length of the rod. This is a uniform rod, so the gravitational force on the rod is acting at the center of mass. Okay. And of course, we've displaced our rod initially from its equilibrium orientation. That is, it wants to hang vertically. In this position, we would consider the angular displacement to be in a counterclockwise configuration. Clockwise. Oops. Okay. While that's happening, so I'm in a counterclockwise position, I'm experiencing a torque from gravity that's in the clockwise direction. That is, the gravitational force wants to restore the equilibrium position, so the net torque produced by the gravitational force is actually in the opposite direction of the position. So what we have is a scenario that the torque will be proportional to minus the angular positions, within reason. I'm just generalizing that. So some factor of angular position, as angular position increases in one direction, the torque increases in the opposite direction. Okay. So that potentially means that we have a what we call a restoring torque. Okay. Of course, for this eventually to be simple harmonic motion, we're going to need a restoring torque that's actually linearly dependent on the angular position. That is, we'd have to be able to write a constant torque equals a constant times theta. So as the positions increase, if theta doubles, so would the torque double. If theta tripled, so would the torque triple. And ultimately, if we create that criteria, then we'll see that we'll get the same fundamental mathematical expressions that we get for our mass spring system, in which we've demonstrated that in class. So let's consider what is the torque by the gravitational force. Well, as always, we consider the line of action as it passes through the gravitational force, and then pursue the actual distance between the pivot and the line of action that forms a right angle. So that's this length here. Basic geometry tells us that the angle here, formed by the line of action and the bar, this interior angle, is the same as the displacement from equilibrium. As such, given that the gravitational force is acting in the middle, we know that that length there is L over 2. Okay. Which means that my base here is going to be L over 2. Opposite is determined by the sine of theta. So my torque, mg, L sine of theta, L over 2 sine of theta, is the magnitude of my torque. Okay, so absolute value signs to express the magnitude of the torque. Again, this of course is equivalent by Newton's second law, the rotational inertia times the angular acceleration. But given that's the magnitude of the torque, we're going to make sure the direction of the torque is also consistent with what values of theta go in here. And for us to produce a positive torque, that is a torque that's in a direct, or for us to produce a torque that's always in the opposite direction of the angular position, we have to account for that with a minus sign. For example, if we consider counterclockwise to be positive values of theta, then sine of those positive values would be positive. But our torque must be in the negative direction, so I would need to put a minus sign in front of this to make sure that my torque is in the opposite direction of my current position. But if I was in a negative position, if I was actually over here, and I had a theta measured to the right in a clockwise direction, that would be a negative value. And the sign of a negative value is negative, but the extra negative sign would produce a positive, which would yield a torque in the positive direction. So in general, the magnitude of the torque is mgl sine theta, but the torque itself as a vector is minus mgl sine theta. And that's equivalent to I times the angular acceleration. Okay. That's Newton's second law, of course. So now we have that, we write then, in the same way, as over 2, of course, that I did with the linear acceleration of a mass spring. I make a substitution for alpha as the second derivative of theta. That is, angular acceleration is achieved by taking two derivatives of the angular position function. So we're close now to something that might look like a second order differential equation that looks very similar to that formed when we apply Newton's laws to a mass spring system. Let's group all the terms on each side. We're going to divide the I over and group all the terms together. And ultimately what we get in the end is second derivative of theta plus mg L over 2 sine of theta, and all that is over I. So we divide the i's through. Conventionally, however, it might not be that the gravitational force is right in the middle of the rod if the center of mass is not located in a rod. Let's say this was a rod that wasn't uniformly distributed but had its center of mass located somewhere else. Okay. The gravitational force would still be concentrated at the center of mass of the object. Okay. Well, that would change the length from where the pivot is to where the gravitational force is acting. And in the initial case, that distance was L over 2, but that distance could be any distance given the position of the center of mass position, depending on the parameters of the rod. That being said, we'll just relabel L over 2 as the variable d. And from here on out, when you see the expression written this way, mgd over I, we think of d as the distance between the pivot and the center of mass of the object. Okay, zoom out a little bit. So I'll say that again. In general, for a uniform rod, the distance between the pivot and the center of mass is half the length of the rod, and that's why we had L over 2's everywhere. But in general, if the rod isn't uniform or the object is not necessarily a uniform rod with center of mass at the center of it, maybe it's some weirdly shaped object. And the center of mass is somewhere here, and there's the pivot. Okay, and it's made to go through simple harmonic motion around, or pendulum motion around some axis of rotation and about a given equilibrium position. So in general, the distance between the pivot and the center of mass is what's responsible for establishing or helping us quantify how much torque is being induced by the gravitational force. So mg times d sine of theta, where here's d and here's your theta again. Okay. Again, if you're told the properties of the object is that it's uniform and the center of mass is actually in the middle, then d can be replaced again with L over 2. So now comparing this to the mass spring system where we have a spring constant K and a mass M, when we apply the second law to this system, we have negative kx equals m d2x dt squared. I'm going to zoom back in here. Okay, let's move it over. And in that way, divide the m's through and group all the terms on the same side of the equation. You get the second derivative of x plus k over mx equals 0. And the conclusion we drew from this particular case in class is that the solutions to this function, or this expression, are given by trig functions, sines or cosines. And we're missing an equals 0 here on this side, so I came up short there. It should be equals 0. The solution to this function is a trig function, x of t equals a sine of omega t plus phi, where the omegas are given by the square root of k over m. And of course, experimentally, we would determine that. And because of that, the period is 2 pi square root of m over k for a mass spring oscillation. This guy we put in the box is almost this, because we see a second derivative of the function theta. We see a constant in front of this term, sine of theta, but we don't have a sine of x here. We just have x. That is, the acceleration of the object has to be linearly dependent on the position, that is the x value, right? Not the sine of x value. You can't have some weird function of x here. So what needs to happen to the sine of theta? Well, interestingly enough, we have a condition we call the small angle approximation. And the small angle approximation solves our dreams. It basically says, in so many words, that if the angle theta is sufficiently small, sine theta itself is approximately equal to theta. How convenient. I won't give you the most rigorous form of this. The most rigorous proof of this requires a Taylor expansion of the sine function. Well, that might not be something we're familiar with, so we won't go there. But in general, a graphical argument is the following. If we zoom in on the sine graph, or you look at a sine graph zoomed out rather, between here's minus pi and pi, it's basically a curved function. But if small theta just means you need a region around 0 that are small compared to, for example, pi. Okay, where to the right is some value of positive theta, to the left some value of negative theta. And when you zoom in on that region, what you're going to get, and this is what's cool about the sine function, this can be shown in general, that once we zoom in on that region, okay, around the center, what we get, in fact, is a straight line. We'll see a straight line. A line with a slope of 1. It says the sine of theta is basically theta itself. So if the rise over run is 1, it says that the points on the y-axis and the horizontal axis are identical. So that only holds when we zoom in to a region where there's a certain degree of linearity to the function. So what does that allow us to do? Well, it's pretty clear that using the small angle approximation, we can write d theta dt squared as mg d over r theta equals 0. And this pretty much looks exactly like this. Now, the only difference is that the constants in front of the variable that we're looking for, x, or theta, is now mg di. And of course, again, the variable of interest, the function of time that we're looking for, is theta as a function of time. The actual physical angular positions of a swinging object as it goes back and forth about equilibrium. The same fundamental functions solve this condition. You have some maximum theta, which will be the amplitude, sine of omega t plus some phase shift phi, where the omega here is the square root of mg d over I, just a constant that's in the differential equation. Which means that the period of a physical pendulum is 2 pi square root of I over mg d. Okay, and that result is in general holds for any shape that you attach to a pivot and allow it to enter simple harmonic motion. For pendulum motion, the angle has to be sufficiently small for it to remain as such. Now consider the special case of a point mass at the end of a string. Okay, this we consider a simple pendulum versus the physical pendulum. And what's special about this scenario is that the inertia is simply equal to ml squared. The distance from the center of mass to the pivot is actually L. Making those substitutions, we see T equals 2 pi square root of ml squared over mgl, which results in 2 pi square root of L over G. There you have it.